All right, let's get started here. So welcome back. Short week this week. Hopefully everyone got to enjoy the long weekend. Okay, so before we begin, I thought I'd hand out a few things. A chart for functional groups, and then your one-page guide to nomenclature. Okay, so keep these in your binder, your folders, just for a handy reference. Physics. All right, so these are some functional groups we'll see, but not all of them, okay? So keep these handy when you're doing your homework, when you're practicing. Here you go. Alright, these are all functional groups. I wish this were just it, but no. Alright. And also I'm pinning out a guide to nomenclature, okay? This is all you need to know for nomenclature, so if you're just lost, don't have your notes. This will be a handy guide for your studies of nomenclature. Okay? You're welcome. Welcome. All right, so welcome back. So use these as reference, okay? Especially when you're doing homework. You can't use these on the exam zone, okay? So next week we have the big first exam, okay? So I think Marcel will hold a review session. So go to SI this week and next week, okay? So you can adequately prepare. All right? And then homework assignments, active, chapter 2. Homework number 2 is due tonight, okay? If you need an extension, let me know. And then chapter 3, I believe it's due next Thursday, so please get a head start on that. Still a lot of problems, but not too bad if you space it out, okay? And then the quiz on Thursday. Focus on what we did last week. You don't have to worry about conformations, okay? But worry about acid bases. So predict which is a stronger acid. be able to write products of acid-base reactions, and hybridization and simple naming. Like if I gave you this hexane, could you name it properly? Simple naming, okay? We'll do more complex naming in lab this week, and that's the sort of level I would expect for the first exam, okay? Conformations, we won't quiz on that before the first exam, but you can expect a conformation type question on the first exam too, okay? So, I believe that's all the announcements I wanted to make. Are there any questions before we start? No? All right. So, what's left here, we're going to talk about alkanes, conformations, naming, a little bit more naming, and then the reactions and physical properties of alkanes, which are not that many, but they're still kind of important for the history here. All right. So last time we left off naming those two compounds. Does anyone have any questions on those? They were pretty long. They had complex substituents. Are there any questions on those? No? All right. So let's just move on here to another example. I don't think I did this one, so let's just start with that. All right. So we have a carbon atom. Oops. Don't want that big of a streak here. Not that big of a stroke. All right. So we still have these type of atoms, okay? All right, bird's feet kind of there. Okay. All right. So let's name this alkane. Okay, so you may think, are these alkanes even real? Yes, they are. You can obtain them. Not through not through like simple reactions though. You really need to dig underground and get some oil and then crack it and hopefully break all the crude oil into compounds like this. So the more branching, the better. The better performance as a fuel in general. But this one is particularly complicated, has lots of substituents. All right, so what's the parent chain here? How many carbons? 11, good. So let's just number that. So we're probably going to start from the left because that's where the closest substituent is, the branching point. 9, 10, 11. Okay. Let's put everything together. So we have mostly simple alkyl substituents, but one of them is not simple. Which one's that? At what position? Carbon 6. Okay, so that's we call it colloquially called bird's feet, but that's the group called tert-butyl. All right. So this has two names. I will not name it based off the common name, which is tert-butyl. I'll go over those groups in a little bit. Okay. So this here we have to name systematically again. So let's take a different color here. 1, 2. So we're going to remember it's complex, so we have to number it as well. And then this substituent right here, this will be called at the 6th position dash parentheses 1, 1. All right. What's the name of that? 1, 1 what? Methyl, but not just methyl, right? How many are there? Di. Yes, di. Dimethyl. And then the end of the chain is 2 carbons. So remember, this is a substituent still. So we don't say ethane, we're going to say ethyl. All right, and that's the whole name for that substituent. Okay? 6-11- dimethyl ethyl. So that's the name of the 6th substituent. This is also known as AKA tert-butyl. So if sometimes this is abbreviated like this, you have it coming off here, carbon, and sometimes it's written as this: T, lowercase t, uppercase B, and then U. So that means tert-butyl. All right. I might not write it this way, but you may encounter it that way from all my resources, from other AI maybe. Okay. So that's just FYI. All right. So let's name this whole structure. All right. So we have ethyl group at 7, and then 2 methyl groups at 3 and 5. All right. Now we have to figure out which ones come first in the naming. Is it methyl, dimethyl, 3,5 dimethyl, or is it 6-11 dimethyl ethyl or ethyl? All right. So remember when we're alphabetizing here, this name we just drawn, this name is not a counter. So that dimethyl is actually part of the original name, okay? So this actually comes first. So let's write this long name, 6-1,1 dimethyl ethyl. All right, what comes next? Ethyl or the 2 methyl groups? Ethyl. What position is that at? 7. 7 ethyl. All right. And lastly, we put the dimethyls here. So dash 3,5 dimethyl. All right. You guys remember the parent name for 11? Yep. Undecane. All right. So that's a pretty long name. I guess it does. I wouldn't ask this such a complicated name. I'll actually make it maybe one substituent shorter, okay? Well, you'll get like a whole line to write it, okay? So don't feel like you can't have enough space. All right, any questions on that one? I think the most difficult part is the thing in parentheses. Yes, Catherine.
Why is it 1,1 dimethyl?
Oh, this one? Yeah, so let's go over that again. So remember, this is a branch off a branch. So this is a branching substituent. It's not linear, so we can't just name it, ethyl. So what we do here is we're going to look at that group, right, and just renumber the longest chain on the branching substituent, and we're going to systematically name it again. So that's why we found the longest chain is 1, 2 in either direction. And then the 2 branching methyl groups are given 1, 1 designations because they're both at the 1 position. So that's why we represent this as 1, 1, 1, 1 dimethyl ethyl. Okay. I'll probably have a chart here where I'll write the IUPAC names for all these branching common substituents. But that's how you would name it because it's complex. Because it's not linear. The branching chain here is not linear. That's why we have to name it a little bit differently, okay? But it does have this common name, okay? So if you do name it based off the common name, I usually don't take off points. But you gotta remember, this is where you alphabetize at the B. The tert-butyl does not count. The tert-butyl is just like a identifier. It doesn't count in the alphabet. So you have to look at the butyl. And that gets even more confusing because the prefix iso is actually alphabetized. Okay, so there's a lot of rules to memorize there. So if I were you, I would just stick to IUPAC if you don't want to memorize those specific rules there. Okay? I wish you were different. Okay? But I'm not the one who came up with these rules. All right, any other questions on that example? Okay, so typical level of difficulty here, this naming one. Expect, at least 1 or 2 substituents. One may be complex, one may not be. Okay, so if we actually use tert-butyl, it actually wouldn't make a difference because it would just come out in front again because of the B. But if we had something like isobutyl or isopropyl, that group would actually come after the ethyl because of I, okay? But tert, seq, you might have heard secondary, seq, those are not counted in the S, and the T there are not counted in the alphabet, unfortunately. All right. So let's just go over now, just summarize the 3 rules for naming. Okay, so here's our rules for naming. 3 rules for naming. All right. So I like to use the acronym LLA. So L, what's the first L stand for, you think? Yeah, longest carbon chain. Okay, good. What does the second L stand for? So I'll give you a hint. It has to do something with the numbers. So for the numbers, what do we want? If it starts with L, do you think it's going to be the higher numbers or the lower numbers? Yeah, lowest possible. Number for the substituents. Okay? All right, good. And then what's A? What do we do at the very end? Yep. Alphabetize names of the substituents. Okay, so those are the main rules. So for linear alkanes, you can't go wrong. As long as you got the name right for the substituents, number them in the lowest number scheme, and then alphabetize the names, then the parent name. That's like the so later on when we talk about reactions, I always say you want to know your nomenclature because that's like the easiest points you can get, honestly. Okay, so if you know nomenclature, there'll always be some kind of nomenclature problem, especially for the first few exams. And then when we go to other functional groups, I'll introduce new names. And there's usually just like one part of it is for naming. Okay. All right. So let's do now let's do an example here. Okay. So let me just. All right, so let's name molecule A. All right, so we're going to get more practice with this complex naming, okay? All right, so just follow me. Okay, you got 2 methyl groups here. You're going to now come the branching chain here. Boom. Here's a chlorine. Boom, boom. All right. And then we're going to have 1, 2, 3. Going to now have 2 groups like so. Oops. All right. Okay, and this group here is actually a bromine. All right, so this is purely for practice. I would actually not test this many complex substituents, okay, on a single compound. But these do exist, okay? All right, so let's find our longest chain. There's a lot of branches we have to consider, a lot of entry points here. So if you think you got the total number, just let me know. All right. Well, there's a few different ones you can do. But I don't think the group on the left there, the first to the left, that carbon with 2 methyl groups there, I don't think that's your starting point. All right, what we get? How many? 9. I can see more than 9. 11. All right. And where are we starting at?
Below the chlorine.
Below the chlorine? Okay.
Oh, sorry. On the far right.
Far right. Okay, I like that one. 1. So remember, we start there. We have 2 substituents on the 1 position. So that's a good. That's probably our starting point. All right. 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. All right. So we have a bunch of halogens, okay, and then we have some methyl groups here, and then one methyl group, I think, just one, right? I see one methyl group. All right, and then some other positions here. We have some complex substituents, okay? At what positions do you think we'll have to name complex? 4. Good, that's 1. And? 7. All right, good. So let's start with 4. So go to number 4, and we're going to number the chain starting from the first point of attachment. So 1, 2, and 3. All right. So at number 4, let's write right here, number 4, in parentheses here. All right, how will we name that one? What's the longest chain in blue? Three, right? What's the name for 3? Methyl, ethyl, or propyl? Propyl. So we're going to put propyl at the end. And then how will we name the substituent off that one? So this is a 2. Good. So 2-methyl propyl. That's it. All right, let's do the same thing for 7. 7 has a branching or complex substituent there. So we label 1, 2. All right, so at 7, what would the name be? 7 dash parentheses. All right, so what's the ending name for this one? Methyl, ethyl, propyl? Ethyl, okay, good. And then the substituent is at what position? Yeah, so 1-methyl. Ethyl. So this has a common name. Does anyone know it? Isopropyl. So you guys know isopropyl alcohol, rubbing alcohol. This is what it looks like. That's found in rubbing alcohol. So that carbon group there, that's called isopropyl. Okay? But remember, you do isopropyl, you have to name it alphabetized after the I, after the I, okay? All right. Now this one here, 2-methylpropyl, that is called isobutyl. Why is it called isobutyl? Well, how many carbon atoms are coming off of carbon 4 in total? 4. So it's a butyl group, but it's not butyl. Butyl would be 4 carbons in a row, right? That's why it's isobutyl, the isomer of butane. All right. Well, there's actually another one, but we're not going to talk about that one right now. Okay. Are there any questions how I named these chains or these branching chains here? No. Okay. So either guys memorize this common name, iso, or the IUPAC name. If you do IUPAC, you can't go wrong. Okay? All right. So we have some other functional groups here. We have bromo and chloro and methyl. All right? So, but these complex substituents here, they both have methyl in the name. So these two will actually go first before methyl because methyl runs out letters after the word methyl, like we said before, okay? But Which substituent should come first in our name? Is it bromo, chloro, methyl? Bromo. And what number did bromo have? 1. 1 bromo. So guys, make some room here. Going to be long. 1 bromo. All right. What's next? What comes after bromo here? Chloro. Good. How many chloros do we have? 2. So 1,9 dichloro. All right, good. All right, now we have to include our complex substituents here. All right, oh, interesting. Okay, maybe I got it backwards. All right, so what comes first? All right, here's how it flips. So if you run out of letters, that actually goes first. I think I said it backwards, okay? So all these have methyl, right? So which one will we put next? Yeah, let's put 2-methyl because they run out of letters, right, after we get the word methyl. So that should probably by default come first. But honestly, guys, if you do it the other way, I probably won't take points off, okay? But I would say put 2-methyl here. Okay. Then what's next after that one? We take methyl ethyl or methyl propyl? Which one? 7 or which one? 7 or 4? Let's see. So let's look at. They both have methyl in their name, right? Then comes the word ethyl and propyl. So which one would come first alphabetically? Methyl ethyl. All right. So we're going to do 7 dash parentheses 1 methyl ethyl. All right. And then we do dash 4 dash 2 methyl. Gosh, see how long this name is? All right. And then what's the parent name for this whole thing? Alkane. So this is a prime example of why we just come up with nicknames for pharmaceuticals. Like there's cancer drug that you get from the yew tree. All right. Well, how it works is it freezes the spindles during mitosis. Okay, so the cancer can't divide. It has like 50 stereocenters, so you can have 50 different designations for its isomers. Okay. And it has a long name. It takes like 3 lines of this naming, okay? Probably more than that. All right, so we just call it Taxol. So we have a brand name, okay? We have common names, so they're more easily referred to, okay? So it's nice if you can write this all out, tell your date. You might sound a little smart. But other than that, no real use besides chemical inventory, okay? So this is probably the longest we'll ever write. Okay, so very long name. But anyways, are there any questions on that? No? All right. So if you were wondering, this is molecule A. All right. All right. Okay. So a few things we're going to still go over here. All right, for alkanes, you can classify carbon atoms, okay? So let's draw a line under here and write classification of carbon atoms. All right, so in your homework, you'll have a question that asks you, okay, look at this carbon atom. What kind of carbon atom is it? Is it methyl, primary, secondary, tertiary, or quaternary? Okay. So methyl, if something is a methyl carbon, okay, we say the carbon here, C, is not bonded to other carbon atoms. Okay? So example of this is methanol, CH3OH. Is this carbon here bonded to any other carbon atom? No. All right? So the series here follows a similar pattern. Primary. What do you think primary means? Yes. All right. C is bonded to one carbon atom. Our example here is methane, H3C, CH3. So each carbon atom here is what? Primary, secondary, tertiary? In this example right now. Both of them are primary, right? They're only bonded to the other carbon atom. Good. So then you have secondary. Okay, so the question would be, you know, here's your compound. I'll draw a bunch of arrows, and you tell me what kind of carbon it is, okay? So make sure you review these. If you don't review them, you might just be guessing, and that's not a good strategy. Okay, so carbon is bonded to two carbon atoms. All right. Our example here is this group. This carbon atom in the middle, bonded to one carbon and another carbon. That's a secondary carbon, okay? So my example would be, you can use that example, but the one I'm going to use is CH3, CH2, CH3. And I'm looking at this carbon underlined. That one is secondary, okay? All right, tertiary. So tertiary in this case means 3. So carbon is bonded to 3 carbon atoms. And the best one we can write here is the tert-butyl group. And that looks like 3 CH3s bonded to the same carbon atom, like so. Okay. And lastly, what do you think quaternary means? 4, yes. So this is any carbon atom that's bonded to at least 4 other carbon atoms, and it has no hydrogens. Okay, so carbon is bonded to 4 carbon atoms. And the only way we can kind of draw this realistically right now is you have 4 CH3 groups attached to the same carbon atom, and the carbon itself has no hydrogens. Okay? All right. Are any questions on that? All right. So you can also have what we call the similar classification for alcohols and amines and amides. Well, amides less common, but amines are common. Triethylamine, that's a tertiary amine. And then alcohols. So this right here, what kind of carbon is this bonded to? Is it bonded to? This alcohol right here. Secondary. So we would call this a secondary alcohol. Okay? All right. Any questions about that? So this will become more important when we talk about reactions, but be able to classify the carbons. This will also be helpful when we eventually talk about spectroscopy at towards the end of the semester. Okay? All right. So let's do an exercise now. So we have the classifications, but now I want you to, so in this exercise here, all right, name the compound, and you're going to classify each of the carbon atoms. So let's name the compound and classify the carbon atoms. All right. Okay, so let me draw the structure. That'll probably be helpful. All right, so look at that structure. Okay. So, all right, why don't we take a few minutes, okay, and try to name it. And then each carbon atom, I want you to draw an arrow to it and put 1 degree, primary, secondary, just write the number and a degree sign. Primary, secondary, tertiary, or quaternary, okay? All right, let's see. The name for bromo. All right, do we all get that name? Or maybe working towards that name? All right, so look at the carbon atoms. Each methyl group is what kind of carbon? What do you guys think? So how about number 1? What kind of carbon is that? Primary, secondary, tertiary? Primary, good. So you can say that for all these methyl groups here. All right. How about carbon 2? What kind of carbon is that? Yes, good. So quaternary. So let's just draw an arrow here. Sorry, that's not an integral. All right. How about carbon 3? What kind of carbon is that? Good. So secondary here. Okay. And then carbon 6 and this methyl group here, still primary. Okay. How about carbons 4 and 5? What kind of carbons are those? Sorry, 4 and 5.
4 secondary.
Good. All right, that's a trick question. How about 5 now?
Tertiary.
Tertiary, good. All right. Is there any questions about how we got those numbers or those classifications? All right.
Can you actually go to 225 trimethyl?
Oh, 2,2,5 trimethyl? Yeah, sure. Okay, so do we agree that at the 2 position, there are 2 methyl groups?
Yes.
How about the 5 position? 1 methyl group? So that's why it's 2, 2, 5 to indicate where the positions are. And substituents, there's 3 methyl groups, so it's right, trimethyl. And then what's the parent name? Obviously I wrote hexane, but does everyone agree? Is it hexane?
Yep.
Okay, good. And the reason why we numbered it from the left to the right, okay? Because you might say, oh, wait, if I number it from right to left, left to right, I still get the same numbers, right? But I will have 5,5-dimethyl instead of 2,2-dimethyl, okay? Sorry, yes. So another trick you can do is take up all the numbers from numbering both ways and find which is the least sum, the lowest number. And if you do that, I can guarantee you that it's from left to right, okay? So if you have an identical numbering scheme, front and backwards, look at the side that has the more substituents closer to the lower numbers. That's the way you go. Okay. So in this case, at the 2 position, I have 2 methyl groups. So that's the tiebreaker in this case. All right. Any other questions? No. Okay. So let's go on here. All right, we'll take a little break in a few minutes. All right, so I'm going to go over the common names for some of these complex alkyl groups we've seen so far, okay? The ones like isopropyl, terbutyl that I mentioned, I'm going to go over them more formally now. Okay. So the last thing we'll talk about naming pretty much here is the common name of isomers of some alkyl groups. All right. So, CH3, CH, okay, CH3. Now, this is bonded at this carbon atom, okay? So, it's fine if you write it that way. Just know that it's bonded through the carbon atom, okay? So, we're going to have a column, common name, and on the other column, IUPAC name. All right, so this common name is isopropyl, like isopropyl alcohol, okay? Household disinfectant. All right, the IUPAC name, like we saw before, 1-methyl-ethyl. So there's 2 things you can do here. Either 1, commit the common names to memory, or 2, know how to name it through IUPAC, which I demonstrated, okay? But practice, it takes a while. Believe me, I did not get it the first time, okay? Then we talk about the other one, the 4-carbon group, isobutyl, CH3, CH, CH3 here, okay? CH2, this is where it's bonded through the CH2 group, like that. So this is isobutyl. Okay, this is called 2-methyl propyl through IUPAC. Okay. So those are the ones we saw in the example. Are there any questions so far? No? All right. Okay, so what if now we weren't attached through the CH2? What if we were attached through the CH? Okay, so let me draw an isomer of butane. So here I want to draw CH3, CH2, and now at this position, the CH, okay, I'm going to have the CH3 branched off here. But now this is where the group is bonded off the parent chain, okay? Now, we can't call this isobutyl because the 2 CH3 groups are not bonded to the same carbon. When the CH3 groups are bonded to the same carbon, that has the prefix iso. This, however, the CH3s are bonded to carbons 1 and 3 on the contiguous chain there. So we can't call that isobutyl anymore. We call that sec or sec butyl. Because if you look at this carbon atom here, okay, so let's just classify these carbon atoms here. Secondary, primary. What about this carbon atom now? Yeah, secondary. So don't ignore where it's attached into the main chain. That doesn't count. So we call it seq-butyl because the carbon at the point of attachment is secondary. So that's why it's seq-butyl. All right. But through IUPAC here, we call it 1-methyl-propyl. So you see the through IUPAC, they're not the same. They're not the same. Different names. So if something has a different name, it's a different compound. All right. So there's two more I want to talk about. Okay. We've talked about tert-butyl. We saw that. Okay. So tert-butyl, as the name implies, what do you think the carbon atom, its classification is now? Tertiary. Tert. So this group here, the tertiary group, has some importance in organic. Its behavior is kind of weird. And that's because you have a lot of carbon atoms bonded together. Okay, so this here, tertiary carbon. Okay, so this is called tertiary butyl, or tert-butyl for short. All right, and then through IUPAC, we name it as 1,1 dimethyl ethyl. Okay. So that's for 4 carbons. So yeah, there's quite different ways you can name the 4 carbon alkyl group. Okay. There's many more, but we tend to not name them. Well, there are names, but we tend to not go over them as much because these are the most common. So the last one I'll go over is called, for whatever reason, this is the 5 carbon one where you have a quaternary center. All right. All right. So what if you have, it looks like a tertiary group bonded through a CH2 and to the main chain. We can't call that tert-butyl. So this is a very old-fashioned name. It's called neopentyl. All right, so that's called neopentyl. So if you have a chlorine on the end there, that will be called neopentyl chloride. Okay, and then this IUPAC name 2,2 dimethyl propyl. So these are the only ones you'll be responsible to know. So either remember the common names. So I'll underline where you alphabetize. For iso, you do the I, and then for the seq-butyls and tertiary, you're going to do it here. And I believe for neopentyl, I think it's still through the N. Okay? But you don't have to worry about this if you do IUPAC. Okay? Just FYI. All right, where's the question? Any questions? Okay, so let me just put a little note here. For our purpose of naming iso and neo are part of the alphabet process. Okay. Seq and tert are not. Okay. So you see sec or tert-butyl, sec-butyl. Don't consider them for the alphabet. You're going to alphabet, do the alphabet based on the alkyl group name. So butyl first, then the rest. Okay. All right. Are there any questions on nomenclature for straight chain alkanes? We'll revisit this a little bit and talk about naming cycloalkanes because they're part of alkanes too. But other than that, well, actually, we're going to revisit now. Okay. So, any questions about naming linear straight chain alkanes? No? All right. Let's take a little break, then we'll start naming cyclic alkanes, okay? If there's any questions, feel free to come ask me. I'm going to use the restroom. All right, just go. What's up? What happened? How many carbon atoms bond to? No. No. Looking at the carbon atom in question, right? Count how many carbons are around it. Bonded to it.
Just this one, right?
Yeah, that's dot carbon. No. Well, how many carbon atoms are bonded to it? No, just look at this carbon atom, right? And look at the 4 rings around it. How many of them are carbon? No. 1, 2. So just 2. Yeah.
No.
Look. Yeah. See? Okay. Anyone not sign in? Jessica. Here, just sign in.
Thank you. I have another question.
Yeah, what's up?
So what I'm saying, this is 1, 2, 3.
Yeah.
1, 2, 3.
Right. Look at the bonds around it. How many of them are
I
carbon
thought we were
atoms?
looking at the.
No. So it's always the carbon atom and
Thank you, Andrew.
yeah, you're welcome. Yes, sir. Anyone else not signing? Catherine?
I didn't.
What's up?
I have a question. Would it be possible then to have like one of the full names where we have one of the common names, but then we use the IUPAC name for other ones? Or is that like if we use one common name, we have to use it?
Yeah, be consistent. So
Okay.
it only for these branched ones, but yeah.
Okay.
If there's 2 branched ones like this, you use both TERT or both, C, TERT, or ISO.
Okay.
So use either both the common names. Don't mix and match. So they'll do
Okay.
one IUPAC and then don't do the other one common name.
Okay. So
That's
just
not
be
proper.
consistent. Okay.
Just be consistent. Yeah.
Yeah, it's only here. Is this the original? This yeah, no, this is over here. So this is double bond. Yeah, I moved this one over here and this one over here because it gets rid of this positive charge, but then this settles. You can just undo it.
Yeah, I guess. Oh yeah, 8 people want to take Alkane. But usually offer to fall. They're trying to get.
This.
Yeah, maybe. I don't know what's going to happen. We'll see. But if I am, I can't teach 2A. We'll see.
So it starts on this carbon.
Yeah, that's too much. I caught one time. That was too much. It's not that bad.
This carbon is double bonded, and then it has two.
So, yeah. So basically, just do all
By
reactions.
moving this double
Yeah,
bond
you got
over
it.
here.
Yeah, no. There'll be more laughs. More
Positive.
Yeah, there's really not much
Carbon doesn't
more.
change because again, the double bond moving over there, they still, it still would become. I do it only until one hydrogen.
See you right now.
Your double bond is moving there. Just reverse. this carbon. This carbon will also have this double bond. Here, this one of these right here, so it still has a double bond. Same thing for this carbon, it doesn't change, which is a carbon. This one is double bond, because now it's getting another bond, now it's neutral.
Unless I add the 3 H.
So this one. We have this originally, this.
Or try.
This carbon, which initially has one hydrogen, and then a double bond. By making this a double bond, it would moving it over here, lets this carbon
Professor.
Hi, what's up?
Okay,
Remind me your name again.
Evelyn.
Evelyn, yes.
Evelyn. Okay, so I did this exactly like Jessica,
Okay.
and it's telling me this.
Good.
Oh, I know what I need to do.
Oh, you do the arrows.
The arrows.
Yes.
How was that? It was the.
You got it? Oh, no, okay, sorry. I thought this crap was an arrow. So it's coming from the base. That's right. And then the nitrogen, right?
And then they get an H.
So another one. NH. N.
N?
So where hydrogen is unique? Or
I know the acid's gonna give the H.
yeah.
And
So
the
which
N.
H? Which H? Choose one.
This one?
Get that one.
Oh,
So that's how the arrows work.
okay.
All right. What's up?
So like I guess I kind of understand like what's going on with like this naming stuff, but I don't understand like how you know when to start.
So you're trying to find the longest chain, right?
But like why do you sometimes like go up? Like I understand like this is separate, so like
Oh, so remember it's always the continuous number of carbon atoms. It doesn't matter if it's a straight line. It can go up and down as long as
like in this one.
as long as the carbons are connected adjacent.
Right. So why did you start the one here and then you started up here?
Well, let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, okay.
Like I
So if we do it this way, we'll have less substituents on the chain. So you want the chain with the most substituents. So this will be 1, 2, 3, 4. This will be this way. 1, 2, 3, 4, 5. So there's 5 substituents that way.
but I mean like for example like if I saw this the first thing I would have done is like I'd be like 1, 2, 3, 4.
Oh, straight across?
Yeah.
Well, that's too few carbons, right? You want the largest number of carbon atoms.
Oh, okay. But then
Yeah,
okay.
that's the first one. Longest chain of carbon atoms. That's 2 carbons.
So why did you start on the right and then on the left?
Oh, so if I did it this way, you mean this going this way? I don't think you have enough. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. You mean this way? Which way? Are you talking about?
Like you started one with the right and you started.
Oh, the chain's too short.
Oh, so it's the same thing.
Look, it'll be 9 carbons. This way, it's 11.
And why can't you put the one down here?
So let's see. 1, 2, 3, 4, 5, 6. Oh, okay. So if we do a 1 here, this substituent now becomes complex. we'll have to name it like this one. See these other numbering here? 1, 2, 1, 2, 3. We'll have to number it that way. And so you want the longest chain that has the most number of constituents coming up. So this will only have 1, 2, 3, 4. So if I go this way, 1, 2, 3, 4, 5.
And the quiz, are you gonna have to do this or just like?
No, simple. Here's the 6 carbons. Give me the name. Hexane.
Okay.
You did, yeah. All right, guys. Let's refocus here. All right. Did anyone not sign in? I know some people are not here. Oh. All right. Oh, I don't think you signed, will you?
Oh, sure, I did. Last Thursday, you had a sign for the last sheet. That's why I meant, I thought it was there.
Oh. Well, you do the whole. Yeah, okay. Sorry about that. All right, Jacqueline here. Oh, yeah. Yeah, sometimes that's why I don't necessarily give you points for this, but if you're here all the time, I might consider extra points. All right, guys. So let's switch gears here. Now we're not naming linear alkanes. Let's go to cyclic. Okay. All right. Actually, yeah. All right. So when you think of cyclic or cyclic, what do you guys think of? Circle, Ferris wheel, right? It has a loop, so both ends are now connected. So on a typical cycloalkane, if it's unsubstituted, you do not have a CH3 group. They're all CH2s. Okay? So let's give some examples. All right. Okay. So this guy here, we don't call it a triangle. We don't call it triangular alkane. None of that. Okay. We have the prefix cyclo, and then the parent name. So what would you call this? Cyclo what? Propane. So cyclopropane has very interesting properties. Its structure is still baffling. Okay, and that's because of how compact the bonds are forced to be in this cyclic arrangement. Okay, so 1, 2, 3. All right, so we could go down the row here. We have now the square shape. That's called cyclobutane. And notice here, it doesn't really matter what order you number it because there's no substituents. So every carbon is equivalent. Okay. All right. So let's do another here. So let's go to. So there's also cyclopentane, cyclohexane. Okay. So be able to draw those basic shapes. Heptane is the hardest to draw. I probably won't actually name that one. Okay. Or draw it. Okay. But the other easiest ones are the stop sign. What shape is that? Octane, yeah. So cyclooctane. So hopefully you guys can count that each end here. So I drew 8 lines, right? So each line represents a bond between 2 carbons. So 1, 2, 3, 4, 5, 6, 7, and 8. Cyclooctane. So there's 2 O's in there. Yes, okay. So now, how do we name, though, more complicated ones when they have substituents? So let's take the 5-carbon. What is this one called? Yes, cyclopentane. Okay. So let's have a chlorine coming out here. Don't worry how I draw it. There's no 3D features yet. Okay. So there's a specific way to number now that we have substituents on it. All right. So you want to work your way clockwise, counterclockwise, where the substituents have the lower number. But you might be asking, where do we start? Okay. So if you number from the methyl, you could go 1, 2, 3 to the chlorines, or you could go reverse 1, 2, 3, starting with chlorine. So here, the name, the first letter of the substituent name will matter. Okay. So I'm actually going to start numbering from this chlorine and do 1, 2, 3. All right. Why do you think I don't start from methyl? So we think of chlorine, right? Does chlorine come first or methyl come first? Chlorine, right? C comes before M. So that's why it's 1, 2, 3. Okay. So we will name this as 1, 2, dichloro. I'm going to put underneath 3, methyl. Cyclopentane. All right. All right, I don't think I have room to write on the right, so I'm going to write it underneath here. All right, so let's draw a hexagon. Okay, so now we have OCH3, CH3 here, H3C. Okay, and then we have a bromine here. Okay, so again, we have to number around the ring where the substituents get the lower number. All right, so where do you think we're going to, how we're going to number it? Where should the number 1 start? Top, bottom, bottom left, bottom right, top right, or top left? Okay, you might think bromine. That's a good first guess. So if we do bromine here, 1, 2, but then both of these get 3 and 3, right? 3 position. Now that's actually not what we want, because if we number the other way, so we now add these numbers up. 3 plus 3 plus 1 is what? 7? That'll be 7, right? So let's actually go back. Boom, boom, boom. Let's do it this way. So now if we have this at the 1 position, 1, 2, 3, both methyl and methoxy will have 1. That's 2 plus 3 is 5. So that's actually the lower sum. So this is the way we should number. All right. So if there's more than 1 substituent on a carbon, and then there's another carbon with only 1 substituent, that should give you, that one with the multiple substituents should have the 1 position or the lower number. Okay. So this is the way we number it. All right. So let's put them in alphabetical order. 3 bromo. All right. What comes first, methoxy or methyl? Methoxy, right? Because it's, whoops, sorry, I didn't spell that right. Methoxy, then 1 methyl. All right, what's the parent name in this case? Not cyclopentane, but cyclohexane. So make sure you could draw cyclohexanes. We're going to see these a lot, and we're going to actually draw them in specific forms. That's called the chair conformation, but that's for another day. Probably not before the first exam, so you don't have to worry about that. Okay. Okay, so let's do one more example. All right, we have a triangle, then a few carbon atoms here. All right, so for this example, let's just try using the common name for some of these prefixes, okay? Or for some of these substituents. All right, so you might be wondering, how do I name this? Is the cyclopropane a substituent, or is it the parent chain or the parent carbon compound? All right, so a lot of rules have changed over the past. I'm just going to keep it straightforward here. When you have a linear chain and a cycloalkane, the cycloalkane is always the parent chain, okay? So this is actually going to be an alkyl cyclopropane, okay? So first, let's write that. This is actually some cyclopropane. All right. Okay, so let's number the carbon atoms, okay? All right, so we have a cyclopropane. 1, 2, 3. Okay. So you might be wondering, how the heck do I name this alkyl chain? Well, it's going to be complex. Okay. So now let's number in a different color. Okay. So we know it's a cyclopropane. If it's at the one position, if it's only like substituted at one position, you don't have to indicate the number. So we're just going to put the name in parentheses, okay? So let's number at the point of attachment. 1, 2, 3, 4. All right. Okay. Which way do I go? Do I go down or do I continue going to the right? Okay. Yeah, so go to the right, because this way, now you have two substituents instead of just one. Okay, did everyone see that? If I went down, I would just have the isopropyl group. But now I don't have to consider isopropyl group. I made it more simplistic now. So now it's just a methyl and a methyl. Okay? All right, so how long is this alkyl chain here? 6. So in my brackets here, I'm going to have an hexyl group, right? It's complex. All right, how do I finish the rest of that name? I have substituents where? All right, at 4, what do I have? Good, 4 ethyl. And then at 5, what do I have? Good. Am I going to... All right, sorry. Back up. This is why I don't like drawing it this way, because I don't leave myself enough room. All right, methyl. Okay. And now we can move this back a little bit closer. Okay. So remember, since now hexyl is the parent chain of that substituted alkyl group, we now call it 4-ethyl 5-methyl hexyl, because it's a 6-carbon chain that's attached directly to the cyclopropane. And if you want, you can put a 1 here, but you don't have to. All right. The 1 is optional. Okay. All right, that was a lot. Any questions on that one? So you see here, I made this group here. That's my parent chain, so that's why I kept the cyclopropane. But now the alkyl chain is not completely linear, so that's why I have to name it 4-ethyl 5-methyl hexyl. Okay. If it was just 6 carbons straight in a row, I could just call it hexyl cyclopropane. But I have to indicate where those substituents are at, so that's why I named it that way. Okay, any questions? No. All right. So now let's talk about stereoisomers. So you can have stereoisomers in rings. It's more common in rings than, say, linear alkanes. All right. So we're going to go into the terms cis and trans. Have we heard these terms before? Stereoisomers, okay? So stereo is not like the boombox, okay? It refers to arrangement in space, okay? So if we draw, say we have our cycloalkane here. All right, I'm going to do my best to draw it in 3D. All right, so this is actually pointing down, and this is actually pointing down. So they're both pointing towards towards one face. So let's say this is a triangle. You have the top face and the bottom face. If they're both pointing towards the same face, what isomer is that? Cis or trans? Cis, right? Trans means opposite. Cis means on the same side. So to indicate cis and trans, we put this in front. So we're going to write cis dash 1 bromo 2 chloro cyclopropane. Okay. Do you understand why it's 1 bromo and not 1 chloro? Are we okay with that? Bromo just comes before in the alphabet. All right. Okay, let's do now an example of a trans isomer. Okay. So now in this case, let's use our wedged and dashed notation. All right. Okay, so just looking at this, what do you guys think? Cis or trans? Trans, okay? So this means the ethyl group is going away from us. Sorry, we actually built a model. We can actually see that more clearly. But the dashed, the line bond here, or the hashed bond, that's going away from you. And the bold bond is coming out at you. Okay, so it's like, you have tetrahedral, one's going in the back, one's coming out in front of you. Bold means coming out at you. Okay, so in this case, this would be trans. Trans. Okay. Now the ethyl comes first, so we get that to 1 position. 1 ethyl, 3 methyl. All right, what's the parent name? Cycle what? Good, thank you. All right, let's do a few more. All right. All right, we have a bromo coming in the back here. Methyl groups. Let's see out here. All right. So even though this has more than 2 substituents, as long as you know, relatively speaking, the relationship between the halogens and the methyl groups, you can distinguish between them. All right. So looking at just the halogens, what relationship is that? Trans or cis? Trans. Okay. So in this case, this would be trans. All right. So let's look at the numbering here. Okay. All right. So we're going to start the number here. Is that the bromine or is that the methyl groups? The methyl groups. That's up 2 substituents. So let's do 1, 2, 3, 4, 5, and 6. All right. So this would actually be trans 5 bromo. Okay. 2 chloro. All right. 1, 1 dimethyl. Okay. Cyclohexane. So you have cis and trans isomers. So sometimes you might have to draw both to be able to draw both. Okay? But for like this 4 one here, don't worry about that. That's merely for practice. Well, I might ask you to draw, not on this upcoming exam, but in the future here, is here you have 1, 2 bromo, say 1, 2 dibromo cyclopropane. Draw me the cis isomer. Draw me the trans isomer, something like that. Or convert this back to the name. So be able to draw the structure and then name it too, and vice versa. All right, so let's do, I said I won't make you draw this, but we'll just draw this once. A cycloheptane. So do your best here. All right, so it looks odd. I don't know, I guess it looks like a house, but very oddly shaped one. Okay, so here you're going to have a chlorine sticking out to the front. Then several carbons away, 3 carbons away, you're going to have bromine protruding at the back here. And then right next to the chlorine, also pointing to the back, is going to be OCH2, CH3. All right. So, can you actually, so when you have something like this, okay, it's impossible to designate a trans or cis label. So either you have to have 4, even number, 2 or 4, okay? What I will ask of you is probably only 2, all right? 2 substituents, tell me is it cis or trans. Well, right here, we can't really tell because there's 3 substituents. And depending on which point of reference you're at, you either get trans or cis, okay? So it's too complicated. We're not going to do that. So the one with 4 substituents, it was pretty straightforward because if I was just thinking of the halogens, it's trans. But now, if I look at the methyl groups, they're also trans. So that's why it was unambiguous. But for this one, can't do it. Okay, so you're going to ignore the cis and trans label. All right, but how do we number this one? We're going to, let's see, where should the 1 go? If we give it a bromine, you might have too big of a number. So you might have to reconsider that. So if we do bromine, right? 1, 2, 3, 4, 5. Okay. So keep that in mind. Now let's go back. Let's do chlorine instead. 1, 2, 3, 4, 5. All right, which way should we number? This way or the first way? This way, because this one has lower numbers for chlorine, and that's the ethoxy group. So now we will name this 5-bromo. All right, what comes next? So remember, OCH2, CH3, that's ethoxy. Starts with an E. So what comes first, chloro or ethoxy? Chloro. So 1, chloro, 2, ethoxy. And what's the parent name here? Cyclo what? Good, thank you. Cycloheptane. Very good. All right, any questions on cycloalkanes, naming? We'll get more practice with this, okay? Especially on Thursday. All right. So now we're going to talk about physical properties of alkanes. Not much, but there are ones you should know. All right. All right. So let's talk a few things about them. Solubility. Are they soluble in water? What do you guys think? You have a tanker, gets a hole in it, leaks oil onto the ocean. Does the oil sink? No. It mainly does what? Floats, sits on top of the water. Still not good because some oil will get through to the surface of the water, and the quality of life will then become, especially the birds sitting on the water, they will become, they will need to be treated by a vet. Okay, so not good. So alkanes are not soluble in water. All right, they are soluble in what kind of solvents? Organic. Yes, exactly. Organic, non-polar solvents. So the best way to clean up oil is if you have hexane or pentanes, you spray it on a paper towel and wipe up the oil. That's the best way. Don't use water. Water won't do anything. Okay? So soluble in non-polar organic solvents. These will not be soluble in alcohols. So you might be able to get away with this, but if you use methanol, it won't work. Okay? So it has to be non-polar solvents, namely other alkanes. Ethers might work too. But alcohols, anything with a polar OH bond, won't work. Okay? All right. What can we say about their boiling points? Are they typically high or low? If you think of alkanes in general, think of the lower alkanes. Butane, propane. What are usually at room temperature? Gases, liquids, or solids? Gases, okay? So low boiling points. Gases usually at room temperature. However, as we get more carbon atoms, these will tend to be more liquidy and more solid in the case of fats, okay? So higher molecular weight, you're going to get higher BP, okay? So for example, cooking oil, right? What's the physical state of cooking oil? Is it a gas? No, it's a liquid, right? It's a viscous liquid. So the more carbon atoms you have, you're going to have increasing weak intermolecular forces, and that's what drives the boiling point. Okay? And then if you try, you got bacon one day, and you need to clean up the oil, well, you heat it up high enough, it becomes liquid. What happens when you let it cool down? What does it turn into? Solid fat. Okay? So the higher the boiling point, the more liquid and solid they will get. But usually speaking, the lower range of alkanes we talk about, they're mainly gases. So they have really low boiling points. Okay? All right. So I'll give you a range. C1 to C4, they are gases. All right. All right, and then you have a carbon that's greater than or equal to 19. They are fats. They're usually solids. Okay? So here's a prime example of how the boiling point here is affected by if you're a linear chain or branched. Okay, so let's look at boiling point. So here's a common example of these alkanes. All right. So that's regular pentane. Now this is an isomer of pentane, and this right here is neopentane. So all these three compounds here, they all have the formula C5H what? Just count the number of hydrogens on the left example. How many hydrogens are there? 12. So they all have C5H12, but they have very different boiling points. This is 36 degrees Celsius. This next one, 24 degrees Celsius. And then this last one is a gas under at room temperature. Okay, so very low. So the key takeaway here is branching decreases the boiling point. And that's because when you're branching, these molecules here, they don't like to interact because now they have lower surface area. So they can't interact effectively. So that's why the boiling point tends to go down, okay? So if we look at from this direction, increasing branching at central carbon, all right? The boiling point will decrease. Okay, so one thing I want you to keep in mind is more carbon atoms. So instead I give you a list of compounds, be able to list the alkanes in order of increasing or decreasing boiling point. All right? More carbon atoms means higher boiling point. Now, if they're all the same number of carbon atoms, they will always have the same number of hydrogens. You'll have to look at branching. The most branched has the lowest boiling point. Okay? All right. One thing before we get into conformations again here is that the only other use for alkanes really, besides gasoline, fuels, as petroleum jelly for certain products, especially for your health. It's supposed to house medicine too. That's one use of it. The other use of it is generating energy, okay? So the other thing we could talk about is energy content. So energy content here is dependent on branching, okay? So energy content has a few things you want to look at. More energy released if there is branching. Okay? All right, so branched alkanes are inherently unstable, and that's why they combust so well in your gas tank. Okay? So in your gas tank, you just don't have one alkane. You have a mixture because that blend is the one they tested optimally. They optimized it. And it turns out if you have branched, linear, and cyclic alkanes, they perform better than straight on linear or just unsubstituted cyclic. Okay? So more energy is released if there is branching. Okay? So if you in terms of energy content for gasoline, octane number is determined by isooctane, not octane. Okay? So the more branching you have, the better fuel it is. Okay? And they add all sorts of other stuff to prevent knocking, prevent premature ignition. Okay? So if you don't have those factors taken into account, your gas won't perform as well. Okay? So one thing I want you to keep in mind, more energy, it turns out if your molecule is more branched, you get more energy out of it. Okay? All right. So how do we determine this? So energy content, we determine this. Determine energy content through. All right. So we all taken 1A and 1B. Do you guys remember what kind of device we use to measure changes in temperature? Not a thermometer. Through a chemical reaction, You measure the temperature of the water after a reaction has occurred, and you figure out how much energy was actually released during the reaction. What kind of device did you use? Yes, Drew. Balm calorimetry. All right. So we can't use coffee cup. Why not? Well, when you're reacting alkanes, they don't act like acid or bases. They are going to react and combust in the air. You can't use a coffee cup because it'll explode. Okay, it won't hold your content, right? You won't be able to measure it effectively. All right. So one thing I want to point out is calorimetry. That's how we determine the energy content that's within these alkanes. Okay. So any combustion reaction, there's some energy value that's associated with the reaction. How do we measure it? Balm calorimetry. Okay, so that's one application. Unfortunately, we can't do it here or any CC really because we don't have the right equipment. Okay, balm calorimeters are expensive. They're made out of steel to resist increases in pressure. But that's one other property we can take advantage of. All right. Are any questions on that? So that's the properties, all the properties I want to go over. Boiling point, energy content, and solubility in water. Yes. Oh, yeah. Oh, sorry. That stands for molecular weight. But another way you could think about this is molar mass. All right. So things with higher molecular weight they have higher boiling points. For example, decane has a higher boiling point than pentane because it has twice the number of carbon atoms and hydrogen. All right. Good. Any other questions? Clarifications? No? All right. So, last thing we'll talk about, conformations of alkanes. We kind of touched upon this in lab. So if you weren't, if anyone missed lab, make sure you get those notes. That will be helpful because on this one, I'm not going to go into too much detail, okay, because of time. So conformations of alkanes. All right. So we saw last time, right? If everything has single bonds, what can these molecules do? They can rotate. Okay, good. So alkanes rotate around CC bond. Okay, so that's something we saw, right? And that's why these molecules, they have the energy. When these molecules are moving, they have energy. Some of that energy is from rotations. Okay? All right. So let's first talk about conformations of ethane. All right. There's some problems in your homework where you'll have to look at these conformations. Okay? So there's two ways we can draw them. One of them I went over in lab. Another one I'm going to introduce today, okay? So we have something called Newman projections. So Newman projections are a little bit tricky because students try to look at these without actually building a model. That's why we did that last week. And they don't look at it the right perspective, okay? So you're looking at Newman projection, like say this is my axis, right? Looking through the bond from atom first, okay? So we can say we view the CC bond end on, okay? So we're reviewing through the perspective of the bond. If we were kind of, citing the bond from the atom first, okay? So let's think about ethane, okay? Ethane is this molecule. Imagine we're looking straight on the bond like this. Okay? So, there's two conformations for ethane. What was the first one we talked about? All right, I think I heard it. Starts with an S. Staggered. All right, so staggered here. The first, so let's number a few things. This is carbon 1. This is carbon 2. Carbon 1 is right here. Oops, sorry, let me go back a bit. All right, and this circle here is carbon 2, okay? So what that arrow is pointing to, the circle is the back carbon, and C1 is the front carbon, okay? So let's call this the front. Here's the back. Okay. So now we could draw the H's here. All right, now this becomes a little tricky. Hopefully everyone can see that. All right, so this is actually more helpful if we built it. And when we built it last week, we could see that these hydrogens, they point in these directions. That's why we had that exercise. Okay, so that's the stable conformer, right? That's the most stable. All right, well, what's the other one? Eclipse. Good. So I would say keep the hydrogens the same. Sorry about that. And then rotate the back carbons 60 degrees, and you'll get the hydrogens now looking like they're eclipsed behind the other hydrogens. Okay, so this is called eclipsed because it looks like they're eclipsing the other atoms, right? Okay, so that's Newman projections. Are there any questions so far how we drew them? Maybe in class last week or, right now? Are there any, do we need to clarify anything? No? All right. So the other way we could draw these is something called sawhorse. Okay, so the other way is called sawhorse. I don't know if you guys ever ridden on one of them, okay? Back when we were maybe small. But it's like this thing you could ride on as a kid. All right. So it actually looks like a sawhorse in real life. Okay. So the only difference here is you're viewing the molecules CC bond from an oblique angle. So let me just use an example here. All right. So you might see this on the homework too. So I'm going to just say that right now. All right. So here is, it looks like the Newman projection, but you kind of stretched it out. Okay. So this is the back carbon that we saw in the staggered conformation. Now imagine you draw a line here coming out like that, and then you draw the other carbon's arrangement of hydrogen atoms like this. So if you kind of look at from the side here, you can kind of see that it matches the Newman projection. The one coming down a little to the right, that's the front carbon, and the one in the back, that's the rear carbon. Okay, so you can draw it through sawhorse too. Which one I will probably test though? Newman. Okay, sawhorse is a good way to visualize it too. If this first way, you're not picturing it right away. Okay, so this is the staggered sawhorse projection. Okay, then how do you think eclipse will look like? Well, let's just draw this hydrogen now. Let's just draw like this, and like this. So if I was going for a staggered conformation here, how do you think I'll draw the rest of this molecule? Will I flip anything? No, right? So I'm just going to draw a line again, and then I'm going to keep the hydrogen atoms in roughly the same orientation as the back, so they're eclipsing like this. So you see the first one, the hydrogens are staggered in between. So there's the most distance between hydrogen atoms. They're not eclipsed. But in this one, they are eclipsed because they're in the same conformation, or the same relative positions, front to back. The top hydrogen is lined up with the top hydrogen. The right to the right and the left to the left. Okay, are there any questions on that? No? All right. So let's do an example where we go from staggered to sawhorse to Newman. Okay? All right. All right. So here we have CH3. Okay? So that's how we draw it on paper, right? So how do we draw this in a dash wedged? Well, here we go. We have H. All right. So guys, be able to draw a dash wedge too. Okay? So the hash bond is always going to come to the left. And the wedge bond is typically to the right. This will be more important when we talk about stereochemistry. Okay? But try to draw it this way if you can. So this drawing we call the dash wedge. Sorry, not hash, dash wedged. Okay. Now let's convert this to the sawhorse. All right. So what you're doing really here is you're taking the dash wedge and flipping it on its end. That's the sawhorse. Okay? So let's go from the left to the right. Here's the first H. So this position right here is this position right here. Okay? That one. And now if we do the second carbon in the back here, it's going to be the staggered conformation here. Okay, and this blue carbon is actually this guy right here. So you see how it kind of matches up with the circles that I marked there? So that's sawhorse. All right, so this is, let me just put this in perspective. So this is the staggered view. Okay. Now, then we can convert this to the Newman projection. Okay. H. And here, this bond angle here is how many degrees? Sorry, this is not a bond angle. This is actually called a special name for it. So when you're measuring the angle between two planes, let me just put it that way, this is called the dihedral angle. So what's the value for this angle? 60 degrees. Okay. So not enough time here, so we're going to end it there. Thursday, I'll show you a little video how these conformations kind of link up like we did in class. And then we'll start talking about reactions for alkanes. Okay? All right, that'll be it.